Hello, I'm Nancy Strickland from IT Mentors. This video on parallelism is part of a series on the Beta 2 release of Visual Studio 2010 and the .NET Framework 4. I'll start with a short introduction to parallel computing with the .NET Framework, and then I'll talk about each of these features that support parallel programming in .NET 4 and Visual Studio 2010 Beta 2. The Task Parallel Library, Parallel Link, data structures for parallel programming, and debugging tools. Parallel computing takes advantage of multiple CPUs by dividing the work of an application up into smaller parts, and then wherever it's possible, running those parts at the same time on different CPUs. Now, many personal computers today have dual or even quad cores, 2 or 4 CPUs, and that's predicted to increase. More new computers will be multiprocessor systems, and they'll have more CPUs each. But multiple processors don't help if the software can't take advantage of them to run faster, and that requires parallel computing techniques. So with Visual Studio 2010 and the .NET Framework 4, Microsoft has introduced new features and tools to support the move to parallel computing, and that's what we'll look at in this video. There's the Task Parallel Library, the TPL, that has classes that make it easier to write parallel code. And there's Parallel Link, which is a version of Link, that's language integrated query, that can automatically execute your queries in parallel. Data structures for parallel programming gives you collection classes that are designed to be lock-free and thread-safe for parallel programming. And new parallel debugging tools are part of Visual Studio 2010. Now, I recorded another video on parallelism as part of a series on .NET 4 and Visual Studio 2010 several builds back. It was about 9 months ago when it was still in CTP, the Community Technology Preview. This video updates that material for this latest release, including new features in coding and debugging. The Task Parallel Library includes several new classes that make concurrent programming in managed code simpler and more efficient. We're going to talk about the task and the parallel classes. Parallelism requires subunits of work that don't have to run sequentially so that they can run independently and simultaneously on separate processors. Until now, developers have used threads to run those little units of work, and that worked. But .NET 4 has a new abstraction, the task, and that makes it even easier. There's less detail to manage because the CLR, the Common Language Runtime, manages more of the mechanics for you. Now, the task is a unit of work like a thread, but it's more abstract. It's not directly tied to the underlying operating system threads. And a future is a kind of task that returns a result. The result is computed in a background thread that's handled by the future object. And the future object then buffers that result until you try to retrieve it. If you try to retrieve it before the future's finished computing it, then the thread that's requesting the result will just block until it's finished. Now, whichever you use, .NET manages a lot of the detail work for you at the system level. That's the advantage of using tasks and futures. It automatically distributes your task across however many CPUs are available. And it even does some dynamic load balancing across the CPUs. It keeps an eye on the workload, the CPU workload, and it decides which one to assign a task to maximize the CPU usage and therefore the overall performance. By default, it'll use all the CPUs that are available on that machine, but you can control that in code to use fewer if you want to. So there's several advantages to using task, to moving towards a task-based model instead of a thread-based model for implementing parallelism. It's generally easier to code, and your app will automatically take advantage of whatever hardware resources it finds on the machine it's running on. So that means your app will scale automatically and give you maximum performance for the hardware it's using. Here's what a task looks like in code. You can create the task and start it running with a single Start New statement here, like this one. Now, you may have noticed if you used tasks in the CTP, or if you saw the previous video on it, that I'm now using Task Factory Start New instead of just Task Start New, and that's new in Beta 2. And the argument to the start new method you'll see here is a lambda expression, a method like a delegate that's written in line. And it has the code that the task is going to execute. The code goes where those 3 dots, the ellipsis, where that is. Something else that's new about tasks in the Beta 2 is the cancellation model. If you want to make it possible to stop the task, then what's going to stop it is a cancellation token. The first 2 lines here show how to get a token. You instantiate a cancellation token source and then get your token from it. And then in the loop, you check to see if cancellation has been requested. That's what the throw if cancellation requested method there does. And that's a method, obviously, of the token. And what it does is to throw an operation canceled exception, and you'll then have to write code to catch that exception and do whatever you want to with it. Then when you need to cancel a task from some other location in your code, maybe inside an event handler, you just call cancel on the CTS object, the cancellation token source. That's shown here in the last line, but it could happen anywhere in your code outside the task itself. Now, calling that cancel method doesn't actually directly cancel the task. It just lets the task know that a cancellation has been requested. The task itself has to actually check regularly to see if that cancellation has been requested, and that's why that token throw if cancellation requested method is there. You've got to provide that inside the task. So it's sort of a cooperative effort. The task has to keep checking to see if cancellation has been requested. And then if so, of course, stop itself, do whatever it needs to with that by catching that exception. I'm going to write a little Windows app to show a task and how cancellation tokens work. I've already got Visual Studio 2010, the Beta 2 version, open. This is its new start page. And I'll create a new WinForms project in C#. When it comes up, I'm going to drag 2 buttons onto it. I'll call this one Start. And this one is Stop. Now I'm going to double click that Start button. But before I write code for the click event, I'm going to go to the top here and add a couple of using statements that I need. To use tasks, I have to add the system threading tasks namespace, and then I want to use the sleep method, so I'm also going to add just plain old system threading. And then I'll come down here inside my class, my form, and I'll declare a task, and my cancellation token source, and my cancellation token, and then I want to declare an integer that I'm going to use to set the red element of the RGB background color of my form. And then this integer increment is going to be used to increment the red value there. And now I'll go down into the click method and instantiate the token. Now to do that, I first instantiate my token source. And then I get the token from it. And now I'm going to create my task. and that's task, and then factory. Again, this is new to beta 2 using this factory. And then the method is start new. And that takes a delegate. In this case, I'm using a lambda. And I'm just going to paste the body in here. Okay, there it is. And what's happening here is that in an endless loop, I'm going to continually check to see if the token's been thrown, if it's been canceled. And if so, I'm going to stop, although I haven't written that code in yet. I'll do that in a minute. Otherwise, I'm going to set the background color of the form and then implement the red just a little bit here by that 5 that we set up. And that means the background will get more and more red as this loop continues. And then when it gets saturated with red, when it hits 255, I'll reverse the process. I'm changing the increment to negative and reduce the red until it gets back to 0, which is black again, right? Because I've got 0, 0 for the other two values here. And then there's a little sleep there just to slow it down a little bit so you can see it more easily. Okay, so there is the body of my lambda right there. Oops, got a little too far there. So the start new method takes my lambda, and then the token here is the second argument to it. And then this message box right here is just there to show that the task is ended and the code continued when we run it so we can see where we are. And now I need to show you how you can let the user stop the task, because most tasks just run until they're done, but this particular task is an endless loop, and we're going to let the user choose when to stop it. So that's the code that we're going to put in the stop button click event. So I'll go back to the form and double click the stop button, and then I'm just going to add this little bit of code to that click event. Cancel. Now that call to the token's cancel method is going to cause an exception to be thrown back up here in this task loop. And when that exception's thrown, I'm going to add code to catch it and end the loop. So what I need is what you always need when you're trying to handle exceptions. I'll put a try in around the code that I'm interested in. And then below that, I'll need a catch. And I can catch just any exception, or if I want, I can be more specific because the name of the exception that I'm looking for is the operation canceled exception. And what I'm going to do if the operation is canceled is just break out of that loop and continue on with the rest of the code. Okay, I think I'm going to add just one more little thing here to make it clear what's going on. Okay, so when the user clicks the stop button and we call cancel, then this checking line here will see that cancel has been requested. And then when it throws the exception is caught, we break out of the loop. That brings us down here and it will tell us we've broken out of the loop. However, when we start, because this is a task that we're starting it right here, the program will start the task running independently, so we'll immediately go down to this line and you'll see that the program is continuing after the task starts. So any other code that you have here will continue to run in parallel while your task is running on a separate thread. Then that task will run indefinitely until the stop button is clicked, at which time we'll see the broken out of the loop. Okay, let's see if it's going to build for us and run. Look down here, it's building. Okay, now nothing happens, of course, until I click Start. And when I click Start, you can see that the program continues and the task is started. And over here you can see that that red is cycling. So we know that the task is running independently. And it will run forever until I click Stop. When I click Stop, oops, there we go. When I click Stop, it tells me that now I've broken out of the loop. And so you can see the color's not cycling anymore. And at this point, I'll just end my application. In addition to tasks and futures, the TPL, the Task Parallel Library, also has a parallel class. And the parallel class has methods that make it easy to parallelize your work by using parallel loops and by invoking several methods to run in parallel. It automatically handles creating and terminating the threads you need, and like I said earlier, it's aware of the number of processors available on the machine it's running on, and it automatically adjusts the number of threads that it uses to match that. Now, first of all, the parallel class has for and for each loops that automatically parallelize the work of the loop. So, for example, on the first line here, we have a parallel for loop, and what it does is to call method 1 n times with an argument that goes from 0 to n minus 1. Notice, by the way, that the arguments to a parallel for loop are comma separated instead of semi-comma separated like in a regular for loop. And you see that the third argument here is a lambda expression, and it takes I as a parameter. I is the counter variable for that parallel for loop, and that's automatically incremented, and then it passes that I to the invocation of method 1. It doesn't necessarily have to take an argument, of course. Then the next two lines show us a parallel for each loop. The first argument to the for each loop is an array, and method 1, the second argument there, is going to be called once for each element in that array. Now, in this case, the array happens to be an array of integers, but it could be an array of anything. It could even be an array of objects. Each element in that array is automatically going to be passed into the method 1, so that the method can use that element's value if it needs to. And then in addition to loops, the parallel class also has an invoke method, and what it does is it executes more than one method in parallel. The argument to the parallel invoke is a list of delegates, and I can either provide those individually. That's the first example here, where I've got a couple of different methods that I want to run, and there could be more than two. And then the parallel invoke shows a comma-separated list of each of those methods that I want to execute in parallel. And this again shows them as lambdas and shows me passing an argument to them. And that argument would, of course, have to have been, some value would have to have been placed in that earlier. I can do it that way, or I can set up an array of actions here, or I've got an array of actions called jobs, and there I've got each of my jobs there. And then when I call parallel invoke, I send it that array as the argument to invoke. Whichever way you do it, invoke automatically blocks the current thread until all the methods have returned from the parallel execution, so you don't need to code or wait for it. Here's the code for a little app that's going to invoke 3 methods in parallel when I click the Start button here on the form. Now notice up at the top that I've added System Threading Tasks. That's the namespace I need so that I can use the Parallel class. In earlier versions of the Task Parallel library, the Parallel class was in the System Threading namespace, so this is new to Beta 2. But I still do need using System Threading here because I'm going to use the sleep method. So what I've got here is 3 little methods, job 1, job 2, and job 3, that just sleep for different lengths of time. And of course, this is where your code to do something useful would normally go. And then they show a message box showing that that particular job is finished. And then down here, I'm using parallel invoke to invoke them. And when it's finished, I've got a little message box that's going to pop up and say, everything's finished. Okay, I'm going to run it now, and what you're going to see is the first message box will pop up after about a second, and then the second will pop up about 3 seconds later, not 4, because they're not running sequentially, they're running in parallel. And then, of course, it will say job 2 done. And then about a second and a half later, in other words, not another 5 seconds, they're running in parallel. About a second and a half later, you'll see that job 3 is done. And then immediately after that, it's going to say all jobs done. And the all jobs done cannot show until all 3 of these that were running in parallel are completed, because that's what parallel invoke does. Runs them all 3 in parallel, but won't go on until all of them are finished. Okay, so let's run it and see how it looks. I'll start it. Job 1 is finished. Job 2 is finished. And then immediately the code can continue because all the jobs are done. And now what else I have down here, I'm going to comment out this way of using parallel invoke and uncomment this so you can see the other way it can be called. Instead of calling those jobs directly, I'm going to take the jobs and put them into a little array of actions and then use that with parallel invoke, call it against that list of jobs to be done. Should work exactly the same. Job 1, Job 2, Job 3, all done. LINQ, that's Language Integrated Query, is increasingly popular because it's an easy way to add data querying to your .NET code. And now there's PLINQ, Parallel LINQ, and it parallelizes your LINQ queries. You just use a little extra code, a little different code, to tell LINQ to parallelize wherever it can, and then PLINQ makes the decisions about what parts of your query can be parallelized and how to do it. You don't have to write any of that code yourself. So as this example shows, at the simplest level, you can just add as parallel to your query. And PLINQ can then look and see how many processors are available on your machine and decide how to run your query based on that. So that means PLINQ can run your query differently on different machines automatically, depending on how many processors are available to it. Beta 2 has made changes to PLINQ, but they're mostly behind-the-scenes changes that don't affect how you code it directly. They're mostly related to performance and scalability, along with some individual little enhancements and bug fixes and things. So if you are already familiar with PLINQ from earlier versions, you probably don't have to worry about it at all. If you're just getting started with PLINQ, my earlier demo on parallelism in the CTP of Visual Studio 2010 explains it more and has a demo, and there's also a lot of material on the web and on MSDN in particular. And I've given you some links to get you started on the resources slide that's coming up at the end of this video. .NET 4.0 has some new versions of collections that are specifically designed to support parallel programming because they have thread-safe add and remove operations that avoid locks as much as possible, and if they have to have locks, they use the most fine-grained locking possible so that objects are locked for as short a time as possible. And then because they avoid the overhead that locks cause, they're not only easier to write, but they also improve performance compared to standard collections when you're working with multiple threads. These are the new classes, and they're located in the System Collections Concurrent namespace. First of all, there's the blocking collection, which you use in a situation where one or more threads are writing to the collection at the same time that one or more threads are concurrently reading from it. And then it automatically provides protection so that threads don't fail when they try to add to a collection that's full or read from a collection that's empty. Then there's also 4 concurrent thread-safe equivalents of existing collections. There's the concurrent bag, the concurrent dictionary, the concurrent queue, and the concurrent stack. And these are like their equivalent standard collections, but they have special methods for operations like pop or peek, and that handles the concurrency requirements we were talking about. And then there's also a couple of other useful classes for working with parallel coordination. The countdown event and the barrier help you synchronize work. Now, all of these were covered with demos in earlier videos that are on MSDev. Look in the first series on Visual Studio 2010. It's called A First Look at Visual Studio 2010 and .NET 4.0. You can search for it on MSDev. And then check the videos on Parallelism and the one called An Introduction to .NET 4.0 for demonstrations and more information on these. Visual Studio 2010 has added 2 new debugging windows to support debugging parallel code. There's a Parallel Tasks and a Parallel Stacks window, and they help you visualize and control tasks and thread call stacks during a debugging session. And of course, the best way to understand how they work is with a demo. What I've got here on the screen is a sample project for testing. It's based on a walkthrough on parallel debugging that Microsoft provides on MSDN. And I've given you a link to it at the end of this video in the resources section. I've also posted the project in C# and in Visual Basic versions on my blog, so you can download it if you want. And I'll also give you that link in the resources. I'm only going to use the Visual Basic version for this demo, though it's not really the code that we're going to be focusing on. It's the features of the debugger. Now let me show you kind of generally how the code works. I have a class here, S, and it includes the main method and then a whole bunch of other methods. I'll go down here and show you. There's an A, there's a sub A, sub B, sub C, and it goes on and on. Lots and lots of subs. Now if I go back up here and look at main, you can see that the first thing it does is it gets and prints out the number of processors on the machine it's running on. And then it sets up 4 threads. And then it creates 4 new tasks, each of which start with sub A, and they send an integer to A, 1, 2, 3, or 4. And then it starts each of those threads down here. And then at the end there's a little console read line, because this is a console app, right? So we're just trying to keep the output on the screen. Now just briefly let me show you that the A method calls B with the object that's passed in, so that's the integer 1. And the B method calls, it's the integer 1 for the first invocation, and then 2 for the second, and then 3 for the third, and 4 for the fourth. So that comes in as an object that's passed into A. Then A calls B, passing that object along. B calls C. So what we're doing is we're starting a stack here, and we're already several calls in. Now I'm actually not going to go through the logic of all this code in detail because it's only a demo. It's been written only to be a demo and to have complexity just for complexity's sake. We want a nice stack and threads and such going all different ways because we want to see what the debugger can do for us to help us follow the logic of the program. So let me just say that methods call other methods, and there's conditionals and locks and wait statements and things like that to make it interesting. But I do want to show you one thing, a couple of things here. Down here on line 50, where is it? No, here it is up on line 46. There's a debugger break command. And that's coded breakpoint, so I'm not going to set a breakpoint. It's already there for me in a place where there'll be some interesting things to see. And there's 3 other breaks farther down, and we'll see them in as we start running it. Now, of course, I want to run it under debug. I could just press F5, or I could choose Start with Debugging. And of course, immediately I hit that first breakpoint. Before I go on, you can see that the processor count on this machine is 2, so it is able to do some parallel processing work. Okay, now I'm going to use a debug feature here. Going to go to Debug, and Windows, Threads, and Debug, Windows, Call Stack. And now in the Threads window over here, I can see all my threads. The main thread here is green, and all the worker threads here are yellow. Now on the far left over here, I can see that one of the threads, this one right here, has a yellow arrow, and that means that's the thread that's active right now when I hit that debug, that breakpoint. I can double click on another if I want to make it the active thread, and you can see that there's still a white arrow here to tell me that this is the one that actually was active when it broke. I've just made this current for debugging purposes to get information about it. Now this thread you can see is in a sleep state. Let me go down to these down here, and you can see that they tell me exactly where they're executing. This is in module S, and we're in sub C at the moment. I can manipulate these columns, by the way. I can sort by any column I want, or I can drag them to rearrange them. I can also switch over to the call stack window, and it's showing the call stack for whichever thread I've made current. So that's one of the reasons you have for making them current, so that you can see different call stacks. So if I go over here to one of these, you can see that it's a little small, but I hope you can see that it's in C now, which was invoked by B, which was invoked by A. And now I want to open the parallel stacks window the same way I did the others. There it is. And you can see that I've got a nice little graphic that shows me several call stacks at once. Here's the call stack for main right here. And then here's the call stacks for the other 4 threads over here. At the moment, they're all in the same place. They're all in C, so all those 4 threads are shown together. Now, if I hover over the header for this box, there we go, it'll show me details. It's got the thread ID and the type and which thread is current. The one that's current is the one here in bold. See how it's in bold here? And then in bold right here as well. And then that yellow arrow shows me which thread is current, the bold one. Remember, that's the one I selected is the one that's current. If I hover over it, as you see here, I can also get more information about it and about the other threads. Now, if I go back here to the threads, and I go back and make main the current one, did you see how the highlighting changed here? It tells me where the main thread is because that's the one that I've made current. Now, of course, at any point while I'm in the break mode, I can use any of the other debugging windows. I can come down here to locals, for example. Well, let's go over here. Make something else current. And in locals, you can see that I can see what the value of O is right there. In this particular one, this is the thread that 2 was passed to. If I go to a different thread, and go to locals, this is the one that 1 was passed to. So at any time, I can make any thread the current one, see how it's executed so far through this graph, and view any of its variables. Okay, what I'm going to do now is debug a little farther, press F5 or this, and go to the next breakpoint. Okay, you can see when I did that my parallel stacks window has gotten a lot more complicated. This app was deliberately written to have lots of interesting things going on, lots of branches. But it's definitely easier to understand with a nice graphic like this than through the code. You know that it can be difficult to understand any code, but particularly parallel code, so this helps quite a bit. I can tell, for example, that these 4 threads that were originally in A, B, and C, of those, one went on to D, one went on to F, G, and now it's in H. That's where it is. Again, remember, the current thread is the yellow one, and its path is marked with the blue highlighting. So this is the thread that is currently active when I hit that breakpoint. But there's another thread that is right here, and then 2 more threads out of these 4 went on to I and J. And of those, one went on to K, and the other went on to external code. Now that's code that wasn't written by the user. It's not .NET managed code. It's not Visual Basic code. It's probably part of the .NET framework. And so by default, you're not going to see that because most of the time you're not trying to debug that. That's not what you're interested in. So this shows us that it is in external code at the moment, and it's in a sleep, wait, or join state. And for that matter, so is the thread that's in K at this moment. Now, suppose I want to know a little more about that. If I double-click on this SK thread here, it's going to take me right to where it is in the code. So I can see the code that it's currently executing. It seems to be waiting for a lock at the moment, so now I know why it's in that state. Also, if I hover over it, I can get its thread ID. Oops. Its thread ID there, what the value of the object in it is at the moment, which is 4. Now, once I have gone to it in code, you can see that there's a green arrow in front of it here and a green arrow in front of it in the code. Now, if I try to do the same thing to go to SA, for example, you can see that I get a choice of 4 possible threads. That's because there are 4 threads in there, and so I can choose which one I want to follow. Now, as you can see, the window's getting a little bit messy here, but in a real application, it could be a great deal more complex than this. So you can set it up to show only the threads that you select. Now, to do that, I'm going to click this button right here. It's supposed to look kind of like a blue flag with an arrow, and what that means is show only the flagged threads. Now if I click on it now, nothing shows because I haven't flagged any threads yet. So to flag a thread, I'll go back down here to the Threads Debug window, and this far left column here is the flag column. So if I click on a flag here, then that particular one is going to show up in that window. So I can look at only the ones that I'm interested in, and I can add more threads or I can remove them by clicking over here and look at only the things I want to follow in a less complicated way. Now I'm going to untoggle this so that everything shows again, and then I'm going to press F5 again so I can continue executing to the next breakpoint. This was set as a breakpoint to show you a few different things. One is that this same method L is now in 3 different windows, which we hadn't seen before. Each method was separate, and it's in 3 different windows because 3 different call stacks, because at this point 3 different threads have it in their call stack. Now if I were to click on one of them, then the other 2 over here turn bold so that I can see what all threads also have L in their call stack. Now if I click on the button next to the Show Only flag, this one here, that's the Toggle Method View button. And what it does, the method that I selected, in this case L, is now shown to me with other call stacks, other frames, so I can see which ones are calling into L and which ones L is calling back out. So the graphic is changed to focus on that method as the center of the whole graphic. Now I'm going to turn off the Toggle Method View button, come back here, and I want to hover over this method right here to show you this will auto scroll to the current stack frame. Now right now I don't really need this because the graphic is not too huge, but if this were a really large application, it could easily get too big. So when I select this button, it means that whenever I hit a debug point, this window, this parallel stacks window, will automatically adjust to show the thread that hit the breakpoint sort of in the center of that window. So to do that, I'm first going to make the graphic even bigger by adding to it the external code. That is the code I didn't write myself, like the code in the .NET framework. Now to do that, I'm going to right click here on the surface of the window and put Show External Code. And now the graphic is really large. I really can't even see what's going on. I've got a lot of other frames, but instead of widening the window, let me just kind of show you what's going on there. And now I'm going to make sure that auto scroll is turned on, that it's been pressed down, and I'm going to press F5 again to go to the next breakpoint, and you're going to see this adjust. Watch. It'll automatically take me to the frame that's current. There we go. I hit the next breakpoint, and it said, here's what's going on. It took me sort of to the end of that, the path that's blue, highlighted in blue. And then if I go and I select a different thread, let me select this one here. Whoops. then you can see that the window moved to roughly center on it. And here's another helpful thing. I'm only seeing part of my diagram in the window right now. This little button here in the lower right there, it's hard to even tell it's a button. What that will do is show me a little thumbnail of the whole window, if I could see the whole thing, and then this blue highlighted area shows me what I'm seeing magnified here. And I can drag this around to magnify whatever part I want to. And I can also close this and move around in the graph by clicking it anywhere I want to outside of a frame, right? And just I'm clicking and holding and dragging however I want to. Now this control right here is the zoom control. When I click it, I get a little zoom over here. It's grayed out when you're not actually pointing to it. And if I turn it off, then I can't see it at all. But if I have it here, I can zoom out or in to see as much detail or as little as I want to. Okay, now I'm going to stop this debugging session. I'll just go back up here and stop it. And I'm going to start another debugging session. I'm going to press F5 again. And this time, instead of concentrating on threads with our call frame stacks, we're going to look at tasks. So I'm going to go to Debug Windows and select the Parallel Tasks window instead. Now when I open this window, you can see the tasks. You can see the ID and the status and the location. Actually, you can't see the location. Let me widen that a little bit. Right now, they're all in SC, and those are all task A that's executing. That's the method that's being run. And this shows the thread that's running it with the thread ID. Now again, the yellow arrow shows the current task. I can also change which columns are displayed, or I can rearrange them, or I can right-click up here in the header and change which specific columns are being displayed. And I can make a different task current if I want to, the same way I did before. Again, the white arrow tells me which one is actually executing, because making something current just says I want to get more information about it. Okay, now let me hit F5. We'll go to the next breakpoint. Now you can see at this point that there's a change. A couple of tasks are now waiting instead of running. If I want to know why a thread is blocked, I can just hover over this waiting status and it tells me, in this case, task 3 is waiting on task 4. If I go to 2, task 2 is waiting on an object. It's a monitor, and it tells me that what thread number owns it. It's 3636. So I can see that it's thread 4. Now I'm going back over to open that Parallel Stacks window. And in the upper left corner here, there's a drop down we haven't used yet. I'm going to turn these off. And instead of watching threads, I'm going to watch tasks instead. And there they are. You can see the same features that you did before with threads. You can flag tasks. Whoops, there's our flag. You can use the zoom control. Right, turn it on or off. You can toggle your method view, and that way you can see calls into or out of a particular method. And you can also turn on your auto scroll to move to the current task. Okay, now I'm going to go on with F5 again. And you can see that I now have a new task. Let me move this out of the way so we can see a little better. I'd like to know where this task came from, because it's not one of the original ones. So it must have been spawned by another task. So I'm going to right-click up here, and I'm going to ask to see the parent column, which wasn't there before. And now that I see the parent column, I can see that task 4 is what created task 5. Now, I can look at it this way, where I have to go look at the parent column to see what the parent of 5 is, but I might like to see my tasks in a hierarchical tree. If so, I'm going to if I'd like to see them that way, I could right-click on this parent, and I can select the parent-child view, which is the opposite of flat view. Flat view is selected now, so I don't have it as an option. But I can switch to the parent-child view. And when I do that, see how 5 disappeared? Well, it's now under 4, and I've got this little expansion icon here. If I click on it, I can see 5 as the child of 4. I think that's a really convenient way to see it. And also, if I look over here in the thread column, you can see that they're both running on the same thread. Now let me press F5 again. You can see that we now have some threads deadlocked and waiting over here. And if I expand 2 in my parent-child view here, I can also see that I've got some threads that are scheduled, but they haven't started yet. You can see they haven't been assigned to a thread yet. I'm going to close that back up for a minute. Task 5, you can see, isn't shown anymore. Task 4 isn't expandable, so Task 5 is finished. It's done. Maybe the most interesting thing here, of course, or at least the most urgent, is these deadlocked tasks. And I can get some good debugging diagnostics here. If I hover over 3, it tells me it's waiting on 4. And if I hover over 4, it tells me it's waiting on 3. So I know exactly what's going on here. Now I can also get this information over in my Parallel Stacks window. I can see my deadlocked icons on 3 and 4. And I can also see my running icon here and my waiting icon here. I can also get the same information if I hover over this window that has 4 tasks in it. See how it groups it for me by deadlocked, waiting, and running. And I can also get this information here by right-clicking on the status and saying Group by Status. And you can see it shows me what's running, what's scheduled, what's waiting, and what's deadlocked in a nice little group there. Now I'm going to ungroup them because it's a little more compact. That way I can see what's going on a little better. Now I'm going to right-click a task here in the parallel task windows, and I get some choices. I can copy. That will copy all the information about that thread, and then I can write it out to a document like Notepad or something if I want to save it for reference, like to compare the state of task now to the state of a task at some point later. I can also, if I want to, change to hexadecimal display. All my numbers will be shown in hex. I can switch to the task that I'm on, which is the same as double-clicking it directly. In other words, I'm on task 3, and if I click on that, see how it changes to task 3 for me, same sort of thing. I can also right-click to flag the task I'm on, which is the same as turning the task on right there. Now I'm going to select another task, not make it current, just select it. Right-click again, and you can see some interesting choices here. Freezing this thread or freezing all threads except this. If I freeze this thread, I'm going to click it here. You can see, it might be a little hard to see, but there you go. There's a blue pause symbol here. And now if I were to press F5 again and continue to run the app, the other threads will continue to execute, but this one won't. Or, another choice, let me thaw this one. I'll turn it off again. Thaw it. Now they're all going to run. Or, if I right-click this and said freeze all threads but this, everything else gets the little pause symbol. It's frozen, and this is the only thread that will run. And this is a very nice feature, because if I let only this one task run, I can single step in debug mode through just that thread that I'm interested in. And again, I can unthaw threads so that everything will run again. And there you have it. There's some nice new functionality in the debugger that is specifically designed to support parallel programming. Here are some more resources that you can use to learn more about Visual Studio 2010 and parallel programming. This first MSDN link here will get you to the download site for the Beta 2 of Visual Studio 2010. And then I have a link to parallel code samples for .NET Beta 2. And the next link is for walkthroughs for Visual Studio that include the debugging demonstration from this video along with several others. And for those of you who haven't seen it, the Parallel Computing Developer Center is a great source. It was recently remodeled, and it's always being updated with new content, and that's what this last link here is a link to. The source code for my demos from this video and others are on my blog at the URL shown up here, and I'm also announcing on Twitter as new videos and new demo code get posted. So if you'd like to know what's available and when it becomes available, you can follow me on Twitter at nstrickland1. I hope this video got you started thinking about implementing parallelism in your code, because if you implement parallelism now, then your apps will be ready to scale automatically to the new multi-core hardware that's coming and keep your customers happy. Thanks for watching. Bye-bye.